Hello and welcome to section 4 of our course. In this section, we are going to study dimensionality reduction. Dimensionality reduction is part of unsupervised learning. Unsupervised learning is a category of machine learning which involves dimensionality reduction and clustering. In the next section, we are going to study clustering, and in this section, we are going to study dimensionality reduction. In this video, we are going to study a mainstream technique of dimensionality reduction, which is called principal component analysis. It's a very popular technique. Specifically, we are going to introduce ourselves to unsupervised learning first, and then we are going to introduce dimensionality reduction, and then we are also going to introduce principal component analysis. So let's get started. So far, we have been dealing with data sets that had a target value, and we wanted to match our model output to the target. If we did a good job, meaning that we matched the output of our model to the target very accurately, we got a high score. And the only concerns we had was that were we overfitting and how to regularize and all that. Now, in this case, we are just given raw data. The algorithm tries to learn from raw data without any target, meaning that it doesn't really know the outcome. There's no loss function. All we have is raw data. So we want to learn patterns. We want to learn groups, patterns, hidden structure within the data set, anything that we can extract from the data set in terms of features. Can we reduce the features and still represent the data set perfectly or near perfectly, and so on. Those are our concerns in unsupervised learning. We will cover 3 techniques in this section: reducing the dimensionality of data, meaning that reducing the number of features by identifying the most important features, extracting features from data. This applies to data that is raw, meaning that, for example, images or voice data or text data or something like that. In those cases, we don't have the features already extracted for us. There is no table, and we want to extract features which can explain the data or which can represent the data appropriately. And another technique that we are going to study is clustering. In clustering, we are grouping data by identifying hidden similarities between samples. So we basically group together all those samples which are similar in some way, and that some way is identified by the algorithm itself. So let's discuss dimensionality reduction. We could have potentially millions of features. Think of large images or videos. Identifying features that provide maximum information is important. It is important for reducing model complexity. For example, in our MNIST dataset of digits, handwritten digits, if you remember, all pixels on the image border are always white. So we can easily represent the image borders by a single value, like saying that this is just white, because we know that there's no need to actually include all the pixels in our data of the border. It speeds up training because we have reduced the number of features. We have reduced noise. We have removed noise from the data. So we have features which are left now are actually the ones who really explain the data well. And we have reduced the clutter, and it helps us visualize better as well. Because if we have reduced number of features, we can plot them together against each other easier than before. However, it does result in some information loss, because think like data compression for images and videos. When we compress an image into, let's say, a JPEG image, there is always some loss in the data and some loss in the resolution. Similar to that, whenever we have applied dimensionality reduction to our data set, there is always some loss, because with noise, some real data will be removed no matter how small it is. So when we reconstruct the data back, if we do that, then we would have lost a little bit of information from the data. And this may reduce model performance for a particular data set. It may or may not. We have to be careful, but if we are close enough in our performance to a data set before it was reduced in dimensionality, then we are fine, because in many cases it may be fine to actually have a minor drop in performance and still have a very high accuracy. So in many use cases, it might be fine to simplify our data set and make it more efficient for real world applications. Principal component analysis is a mainstream technique for dimensionality reduction. It breaks down a high dimension data set into a set of orthogonal components. Hope is that these components can explain almost all of the dataset's variance. Variance basically measures how much variety or variability a specific feature has in its values. If a feature has very little variety or most of the values are same or constant, then we don't really get much information from that feature. So it's not really representing anything useful in the dataset. The components that we divide data into deliver an abbreviated description of the dataset. It is important to estimate how many components will be necessary to effectively model the specific dataset by reduced components. Now, without going into a lot of math, we are just going to cover intuitively what covariance means and what eigenvectors are at a very high level, just to give you an idea, because these are the things that are used in calculations of PCA. Covariance is the variance between features. Covariance between two features, x and y, is given as this. Is the expected value or the mean x minus the mean of x. This is x is a feature. Y minus the mean of y. Y is another feature. Multiplying together the two differences and then taking the mean of those multiplied differences again. That's the covariance between x and y. So this measures how the x and y are varying together. If we calculate the covariance between each pair of features, we get a matrix, just like the correlation matrix we had. Eigenvectors are obtained from covariance matrix. So eigenvectors are a concept of linear algebra. It comes under a technique called as singular value decomposition. We are not going into details of that, but just to give you an idea, eigenvectors are vectors or arrays that don't change their direction when a linear function is applied to the covariance matrix. So we apply a linear function to the covariance matrix that we obtained, and there are algorithms for obtaining the eigenvectors, and we get a set of vectors. So eigenvectors are a property of a specific matrix in question, and in this case is the covariance matrix. Related to eigenvectors are eigenvalues, which are roughly equal to the length of eigenvectors. So every matrix, which is a bunch of values arranged in a two-dimensional array, has a set of eigenvectors possibly specific to that matrix, and eigenvalues are the length of those eigenvectors. PCA algorithm identifies orthogonal components, which are combination of features at right angles to each other. So each component is an eigenvector, and orthogonalization is the key in PCA. Whenever we have a vector, just like eigenvectors, we have a direction associated with it. If you remember from the basic mathematics, every vector has a direction. When plotted in a hyperplane, like a 2D plane or a 3D plane or a 4D plane, no matter whatever the number of features we have, we could imagine eigenvectors which are at right angle to each other. So we obtained a bunch of vectors and we considered only those vectors which are orthogonal to each other. Because if they are in the same direction to each other, then they won't really give us much help in actually identifying the components that we are trying to achieve. For each orthogonal component, we calculate the proportion of variance of the whole data set represented by the component. So each component is contributing to the overall variance of the data set because we obtained eigenvectors from the covariance matrix, remember? Then sorts the components by decreasing order of the calculated proportion it is contributing to the overall covariance. And then it takes the top n components where n is specified by the user. So the user gives as input how many components the user wants to divide the dataset into. So this is just to give you an idea of how the PCA algorithm works at a very high level. But hopefully you got the intuition. Basically, we are dividing the whole dataset using the covariance matrix and the linear algebra and singular value decomposition and associated eigenvectors and eigenvalues, and then calculating the contribution of each eigenvector or the set of orthogonal components to the overall variance of the dataset, and then taking the top end.